when we talk about, let's say, with your tissues, what does someone's skin feel like when they're dehydrated versus what does someone's skin feel like when they've got too much fluid in their cells, edema? Is there a difference there? Well, yeah, there's a huge difference there. You look at somebody and say, oh, wow, look, your arm is all swollen. And, clinically we use the term, wow, you've got a lot of edema, okay, in your arm. Versus you look at somebody and say, well, okay, you look shriveled up like a raisin, okay, because you're all dehydrated. Yeah, there's a huge difference in terms of how those cells look. And when we look at how a cell changes based on this concentration, we use a term called tonicity. And we use the term hypertonic versus hypotonic to describe the concentration of these solutions that results in these changes. Because water can pass that cell membrane, we got to control how much water flows into your cells, edema, versus how much water flows out of your cells, dehydration. You think about a daily basis, you have about 2.5 liters of water flowing or going into your body, and you have about 2.5 liters coming out in various ways, through sweat, through urination, through defecation, through breathing out. Okay, you have all different ways. Urine is your big one, of course. So you have all sorts of water coming in from what you eat and drink, and then you have all sorts of water going out in various ways. So about 2.5 in, 2.5 out. Do we need those to be equal? Well, sure we do. If we have more going in than coming out, edema is our problem. Okay? If we have more going out than coming in, then dehydration is our problem. And so we do run into that in terms of changing these cells. So when we describe something in terms of its concentration, and we use the term tonicity, a hypertonic solution is high concentration or highly concentrated. If a hypotonic solution would be one that's low concentrated, hyper meaning high, hypo meaning low. Iso, okay, meaning equal. So isotonic means that water's not going to move. Hypertonic it will, hypotonic it will, and we'll describe that a little bit. Now, when we describe those, and maybe the way to reflect that a little bit, okay, and I'll draw this a little bit, but basically what we're trying to say is what happens to these cells. So I mentioned that we can get it to swell, we can get it to shrink, okay, and that's the changes that are going to take place. So let me come back to what we were trying to get through, and that's what you're seeing here. Now, two terms you want to or a term you want to understand. When we shrink down these cells, we refer to them as crenated cells. Okay, and we'll talk about why hypertonic does that. Here would be a normal red cell is what we're actually showing here. So here would be a normal red blood cell. Here would be one that's lost its water. It's all dehydrated like a raisin. And then here's one that's swollen, and it can actually lyse. Now the term lyse just simply means we get the breaking or the rupture of those cells. So when you get cellular lysis, okay, you get rupture of those cells is what we're referring to. You may even hear of somebody who has, for example, a hemolysis or a hemolytic disease. Bacteria, that's exactly what they do. You have nutrients inside your red cell that are very important to that bacterium doing what it wants to do. And so what it'll do is the bacterium has toxins that will rupture your red cells to release its food so that it can divide and do its bacterial thing. Okay? And that's actually some of these bacteria that are getting kind of really smart and really strong in terms of their ability to do more to us than we can do to them. Yeah, that's part of their process of how they divide so well. Is they rupture our red cells. They lyse them with what we call hemolytic toxins to be able to release that food. So hopefully that makes a little bit of sense. Now, the relationship I want to make here is, okay, let's say go back to my drawing, I have a beaker of water, okay, and inside that beaker I'm going to reflect a red cell. Okay, so here's my beaker, here's my red cell. I essentially have two solutions separated by a semipermeable membrane. Okay, true. Okay, I have solution A outside the cell, solution B inside the cell. So this would be my extracellular water, and then inside this red cell, and the reason I put this little C in the middle to try and make it look like your red cells are not spherical. Okay? They actually look like a donut, but the hole doesn't go all the way through. And so that's what I'm trying to reflect. So anyway, that's my red cell. And so I have extracellular water, and I have intracellular water, okay, inside. So I have two solutions separated by a semipermeable membrane. Semipermeable membrane, of course, being the red cell membrane. And I'm saying that these two solutions are isotonic. Well, what did we say that meant? That means that their concentrations are equal. Now, obviously, okay, this is my liquid in my beaker. Obviously, their volumes are not equal. I don't care. I only care about concentrations. So the concentrations are equal. Therefore, will water move from A to B? Yeah. Will water move from B to A? Yes. But the net movement of water, okay, the net movement of water will be 0. In other words, I'm going to get some moving in, some moving out, but no change. Therefore, will my cell shrink? No. Will my cell swell? No. Okay, so those are equal, okay, with isotonic. Now, let's look at hypotonic. Now, the question is, which solution, we know hypo means low. Which solution are we referring to? Now, in your body, when we want to know the concentrations of solutions, do we look, when somebody comes by and wants to take fluids from you, okay, are we looking at the intracellular fluid concentrations, or are we looking at the extracellular fluid concentrations? Well, they're going to stab you in a vein. They're going to stab you in an artery. They're going to do a lumbar puncture. They're going to do a joint aspirate. They're going to do a bunch of, there's different ways we can stick people with needles. Do we ever really stick the intracellular environment? No, we don't. When they draw your blood and want to look at your sodium level, potassium level, glucose level, whatever, they're drawing your blood. That blood is not inside your cells. It's in your vessels. That's it. So it is extracellular. So when we use the term hypotonic and hypotonic, we're going to look at what is the extracellular fluid and its relationship and concentration to that intracellular. So now we can hopefully apply it to my graphic, which says, basically, okay, if I have a hypotonic solution, that means that solution A, its concentration is low, versus B, okay, which concentration would be high. So which direction does water want to move if that's the scenario? Well, if the concentration is low outside, high inside, then water, where there's more water, osmosis, the net movement of water is going in. Therefore, the cells will swell. Okay? Versus if I have a hypotonic hypertonic solution outside, concentrated, versus solution inside, okay, lower, where does water want to move? Water wants to move where there's, okay, where it's more dilute, okay, quote unquote more water. Okay, so if it's lower here, it's going to move, water's going to move out of my red cell and into my fluid. Therefore, my cell's going to shrink like a little raisin. Okay, so with hypertonic, okay, I get crenated, and do know that term. Crenated is my shriveled up red cell. I get crenated red cells. Now, we can relate this a little bit to taking care of patients. Okay? When we give somebody an IV solution, where do we put that IV? Well, it's called an IV for that reason. Okay? It's an intravenous solution. So we're going to give them a bag of something, and there's all different bags of stuff. Okay? We're going to give them a bag of something into their bloodstream, into their extracellular environment. What if I give them an isotonic saline solution? Okay, saline is a salt solution. If I give them an isotonic saline solution, okay, so I give the person an isotonic solution. Am I going to cause their cells to swell? No. Am I going to cause their cells to shrink? No. What if somebody has edema going on and I want to draw water out of their cells? Can I do that? Yes, I can. Okay, because they are edematous. If I want to put water into their cells, can I do that? Yes, I can. So do we use hypertonic IVs and hypotonic IVs and isotonic IVs? Sure we do. And it relates to how do we want to manipulate, okay, the movements, okay, of these fluids is what we want to do. And so we can see in various solutions. So here's a better example than what I can draw, okay, in terms of this. So if I have an isotonic solution, concentrations outside and concentrations inside are equal. Therefore, no net movement of water is 0, equal going in as going out. They don't shrink and they don't burst. Okay, over here, I have a hypotonic solution. Okay, it's pure water surrounding these cells. And so the water wants to move into the cells, trying equal concentrations. Versus over here, okay, I have more particles in the solution. It's hypertonic. So water wants to move out of the cells to try and dilute down its neighbor, okay, is essentially what's taking place. So they're going to lose the water, okay, and shrink down. Now this is probably the easiest one for you to understand. Just think of a filter. Okay, like a coffee filter. Somebody puts the coffee granules on one side, the water flows through the other side. The water can pass the filter, the coffee granules can't. Therefore, okay, we get coffee flavored water. Okay, is that a way to say it? Coffee flavored water. Anyway, we get coffee on the other side because the granules can't pass. Okay, and you'd probably get mad if the granules could, because okay, then it looks like you chew tobacco because you got the granules all in your teeth. But still, okay, as it passes through. Okay, we're limiting it based on particle size. So we're not limiting it in other ways. We're just limiting it based on size, and that's how our filtration occurs. Now, the biggest place in our body where this happens is actually our kidneys are a great example of this, where we're going to filter our blood. And so it's interesting with our kidneys. We think, okay, our goal is to make urine. That is true, but when it initially filters our blood, we solely filter based on size. So initially, through our kidney filters. And they're called glomeruli, or a glomerulus being singular, as the blood passes through glomerulus to be filtered. Is there bad molecule waste products going through there? Sure there is. But is there good stuff coming through? Sure there is. And so we use the rest of the process to try and get the good back out and let them back out of there and let the bad continue on. And so we get to that process, of course, when we get to the urinary unit. So make sure you remind yourself of understanding, okay, the colloids, solutions, colloids, and suspensions, because that plays a role in terms of diffusion, facilitated diffusion, filtration, okay, and some of those things. And so here what you can see, this is actually an electron micrograph of a kidney. This is actually a rat kidney, but still has similar structure, where here's my filtration barrier, okay, here on this side. Here's my red blood cells. So I know this is the blood side. Well, that barrier doesn't allow red cells through, and that's what's good because we don't like red cells leaving through our urine. Okay, kind of freaks us out just a little bit. But we also have other stuff through here. So this membrane only allows certain things to pass. Again, strictly based on size, which is what filtration is. And then we'll get into active transport, which becomes very important to us in terms of what takes place. All right, thank you.